Hi everybody. This is the lecture on section 5.3. It is on the integral test. So, given a function f of x defined for all x bigger than or equal to 1, say, okay, let's compare the integral from 1 to infinity fx and the sum n equals 1 to infinity fx. Okay, well, the sum looks like this. So here would be, say, f of 1, f of 2, f of 3. So if f of 1 is up here, right, then this area, this is 1, 2, 3, 4, 5, 6, this area is f of 1. And this area here would be f of 2, height f of 2, width 1. And then this area here would be f of 3, f of 4, so on and so forth, like this. Let's leave that one out. Now, the function, is more of a, on all real numbers, is more of a smooth curve, right? But the series is only considering just the integer values, or the values at integers. Still didn't get that right. There we go. So what does this picture say? Okay, this picture shows that, right, the sum n equals 1 to infinity fn is greater than the integral from 1 to infinity fx dx when f of x is a decreasing function. Positive and decreasing function. I could draw a similar picture where instead of drawing the triangle or the rectangles extending out to the right, I can draw them extending back to the left. Like so. This is f of 1. This area is f of 2. This area is f of 3. This area is f of 4, and we can just leave that one out. So what does this picture show? Right, so the first picture shows the series as something larger than the integral. And this picture shows the series as something smaller than the integral. Well, I mean, it can't be the same thing, the same series. It changed just a little bit. Right? We just took off the first term. The sum n equals 2 to infinity is bigger than or equal to the integral. Okay, so the integral it bounds the series below and it bounds the series above. All right, so the sum, let's see, the sum n equals 2 to infinity. Well, let's not write the whole thing there. Okay, so the series is bounded below, except for the first term, is bounded below by the integral, and it's bounded above by the integral. So that tells you that when the integral is infinite, the sum is infinite. When the integral is finite, the sum is finite. So in other words, both the integral and the series converge, or both the integral and the series diverge. So this is known as the integral test. So these two facts yield the following. And that is, if f of x, did I not turn the thing around, is less than or equal to. All right, so the series, the integral bounds the series from above, and it bounds the series from below, give or take one term. If f of x is a positive and decreasing function, only if it's positive and decreasing, then either the sum n equals 1 to infinity fn and the integral from 1 to infinity fx both converge, or the sum and the integral both diverge. So, not that when they both converge, they're equal. They're most certainly not equal. But they either both converge or both diverge. And when they both converge, they're definitely unequal. I mean, the integral and the series are obviously different, right? The area under the red curve is the integral, and the area of the rectangles is the series. Right? And those are two different things. But we can do the following. So, does determine if the series converges or diverges. And let's look at the series sum n equals 1 to infinity. 1 over n natural log n, like that. So determine if the series converges or diverges. Well, let's consider the integral from 1 to infinity. Well, actually it's going to have to go from 2. The integral from 2 to infinity, 1 over x natural log x. Right? So this is the limit as t goes to infinity. The integral from 2 to t, 1 over x ln x dx. Okay, let's find out what this antiderivative is. Okay, so let's do that separately. So 1 over x natural log x, we're going to let u equal natural log x. So du is 1 over x dx. So what we get here is 1 over u du. So the antiderivative of this is natural log of the natural log of u. Plus c. Okay, and we're dealing with positive arguments here. Natural log of u, which is natural log of x plus c. Okay, and we're dealing with positive values of x, so the natural log, well, positive values of x bigger than 2, so the natural log of x is always a positive number, so we don't need any absolute values. So this is equal to natural log of natural log x, limit as t goes to infinity, from 2 to t. So this is the natural log, or the limit, as t goes to infinity, natural log of t minus natural log of 2. Right, but as t goes to infinity, so does the natural log of t. So does the natural log of the natural log of t. So this is infinite. So the integral diverges. So the series sum n equals 2 to infinity 1 over n ln n diverges as well. Okay? So that series diverges because the associated integral diverges as well. Either they both converge or they both diverge. Okay. Interesting example here. So given p bigger than 0, the sum n equals 1 to infinity 1 over n to the p is called a p series. Okay? For p bigger than or equal to 0, bigger than 0, fx equal 1 over x to the p is a continuous and decreasing function. Or sorry, is a positive decreasing function. It's continuous as well, but that doesn't necessarily matter here. In section 3.7, we found out that the integral 1 over x to the p dx from 1 to infinity converges for p bigger than 2 or no, p larger than 1, and diverges for p's between 0 and 1, including the 1. Therefore, by the integral test, the sum n equals 1 to infinity 1 over n to the p does the same thing. It converges for p bigger than 1 and diverges for p between 0 and 1, including the 1. Okay? So the integral tells us all about the series as long as we can actually calculate such an integral, or we have that the series that we're summing up is defined for all real numbers, which of course it won't always be. All right. Next. Let's go back to that picture that we were looking at before. Well, before that, let's talk about estimating sums. So, given an infinite series, sum n equals 1 to infinity a n, for which, well, not for which. Given an infinite series like this, consider the kth partial sum and the kth, what's known as remainder. So the sum n equals 1 to infinity a n is equal to the partial sum n equals 1 to k a n plus the sum n equals k plus 1 to infinity a n. This is the kth partial sum, and this is the kth remainder. And we'll call it Rk. And this is the kth partial sum, Sk. One moment. Okay. So the entire series, the sum n equals 1 to infinity, is the kth partial sum from 1 to k, plus the kth remainder, the sum from k plus 1 to infinity. And the idea is as follows, is if we can guarantee that the kth remainder is small, then Sk will be a good estimate for the entire series, the sum n equals 1 to infinity a n. Right, so most of the sum is in the kth partial sum for k big enough, and the error is the remainder. Okay, so how does that look? How can we guarantee that the remainder is small? Well, we draw a picture like what we did at the beginning. So let's copy and paste, perhaps. No, I'll make a new picture. Okay, so here is k plus 1, k plus 2, k plus 3, like that. And let's say the height here is fk plus 1, fk plus 2, fk plus 3, like that. All right, here's f of k plus 1, f of k plus 2, f of k plus 3. So the blocks represent the kth remainder, and again, dealing with a positive decreasing function like this, the red indicates the function fx. All right, so this picture says that the remainder Rk is bigger than or equal to the integral from k plus 1 to infinity fx dx. But using a similar trick as before, right, instead of drawing the boxes to the right, we draw the boxes to the left, like this. K plus 3 says k plus 4. So if we draw, instead of drawing the boxes out to the right, we draw them out to the left, then we get this picture here. All right, so here, and the red is f of x, perhaps I should label that. This picture says that the integral from k plus 1 to, or sorry, the remainder, no. This is not what we were looking for. We want to go back this one as well. Okay. So then this is k. And here's f of x. All right, so now the boxes, again, they represent the kth remainder. So this time the kth remainder is less than or equal to the integral from k to infinity. All right, so we're doing the integral from k to infinity of fx dx. Right, so what do we have? That rk is less than or equal to the integral from k to infinity fx dx and is bigger than or equal to the integral from k plus 1 to infinity fx dx. All right, so now really the upper bound is the more important one. Is the more important one for our purposes. So let's give an example of the usage, okay? So I want to estimate the sum n equals 1 to infinity 1 over n to the 10th, say, with 3 decimal places of accuracy. Okay, so I want to estimate that with 3 decimal places of accuracy. So in order for the partial sum (1 over n to the 10th), the sum from 1 to k, to estimate the sum n equals 1 to infinity 1 over n to the 10th with 3 decimal places of accuracy, we need that the kth remainder satisfies the following. So the kth remainder is the difference between the partial sum and the entire sum. So the kth remainder, as we said, is less than the integral from k to infinity fx dx. So as long as that, and we want 3 decimal places of accuracy, so we need that to be less than 10 to the minus 4th for 3 decimal places of accuracy. Okay, usually that's enough. As long as you don't have like a 9 in the 4th decimal place. Or the partial sum. Right, so this will say that the first 3 decimal places are accurate, and as long as the partial sum doesn't have a 9 in the 4th decimal place, then there won't be any sort of carryover error. Okay, so I'll make sure that I don't ask any questions in which that happens, but let's see how we're going to do this. Okay, so the error of the kth remainder is less than the integral. So as long as that integral is less than 10 to the minus 4th, then the remainder will be less than 10 to the minus 4th. Right? And the remainder, why are we doing this? Is because the infinite sum is equal to the partial sum, right, the partial sum plus the remainder. So as long as that remainder is tiny, right, less than 10 to the minus 4th, and this gives you a lot of accuracy in estimating this. Okay, that's the idea that we're working with here. Okay, so let's start with this inequality here. Okay, well, the integral from k to infinity, 1 over x to the 10th, we want that to be less than, right, 10 to the minus 4. So antiderivative here is what? That's minus 1/9 x to the negative 9. Oh, I need to set up a limit. So it's the limit as t goes to infinity, minus 1/9 x to the minus 9, evaluated from k to t. And again, we want that less than 10 to the minus 4th. So this becomes minus 1/9 x, or t to the minus 9, plus 1/9 k to the minus 9. And we're looking for the limit as t goes to infinity. And we want that to be less than 10 to the minus 4th. Okay, well, as t goes to infinity, this is 0. And as t goes to infinity, well, this is k. It's not t, so it's not doing anything. So this one goes to 0. This one just is that expression right there. 1/9 k to the minus 9 is less than 10 to the minus 4th. Okay, so now let's solve for k. So 1/9 times 10 to the 4th is less than k to the 9th. So now take a 9th root. So 10 to the 4th over 9, 9th root of that is less than k. Alright, so let's get out a calculator. 10 to the 4th is 10,000. So 10,000 divided by 9 to the 1/9 power equals, so 2.179 less than k. So which k should we pick? So let's pick k equal to 3. So the third partial sum will give us, or should give us, the desired accuracy. Right? K is going to be bigger than this. So you can't pick k equal to 2, because 2 is not bigger than 2.179. You have to go up a step. Right? You always have to round up in this case. So let's calculate that. All right, so the sum n equals 1 to infinity, 1 over n to the 10th, is approximately equal to the sum n equals 1 to 3, 1 over n to the 10th. So this is 1, for n equal to 1, plus 1 over 1,024, plus 1 over, gosh, I don't even know what 3 to the 10th is. 3 to the 10th, 59,049. And this is equal to what? So 1 divided, or sorry, 1 plus 1 divided by 1,024 plus 1 divided by 59,049 equals 1.0009. Oh, we've got a 9 in the fourth decimal place. Well, let's go with that. 1.00099 something something something. Okay, this would be an estimate accurate to 3 decimal places if there wasn't a 99 here. In the fourth and fifth decimal places. So let me see, how can we fix this? Let's go with, instead of 3 decimal places of accuracy, let's say 4 decimal places of accuracy, or maybe 5 decimal places of accuracy. Okay, so for 5 decimal places of accuracy, you need this is less than 10 to the 6th. 1, 2, 3, 4, 5, 6. So as long as there's not a 9 in the 7th decimal place for the partial sum SK, this will work. All right, you won't get any rounding errors. So 10 to the minus 4, or 10 to the minus 6, 10 to the minus 6, 10 to the minus 6. So then this is 10 to the 6, which is 1,000,000. And then we're going to take the 9th root of that. Okay, 1, 2, 3, 4, 5, 6 divided by 9. So 3.636. So let's pick k equal to 4. Let me double check that. 1,000,000 divided by 9 to the 1/9 power, 3.636. So we'll pick the 4th decimal, or partial sum. So the sum 1 over n to the 10th is approximately equal to the sum 1 over n to the 10th, the 4th partial sum. So 1 over 4 to the 10th So 4 to the 10th, 1,048,576. All right, so this is equal to, so we'll do it again, 1 plus 1 divided by 1,024 plus 1 divided by 59,049 plus 1 divided by 1,048,576 equals 1.00099 for something, something, something. Well, 4, 5, 1, something, something, something. So this, with these 6 decimal places, goes all the way out to here. And this boxed number represents the entire sum of the sum n equals 1 to infinity, 1 over n to the 10th, with 6 decimal places of accuracy. Okay? Or this is 5 decimal places. All right, let's go over this again. With 5 decimal places of accuracy, we need that the kth remainder satisfies this, right, times 10 is less than 10 to the minus 6th, and there is no 9 in the 7th decimal place. 5 decimal places of accuracy. So this one. All right, so the box number represents an estimate of 1 over n to the 10th, the sum from 1 to infinity, with 5 decimal places of accuracy. Because over here in that last decimal place, here in the 6th decimal place, there isn't a 9 there. So because there's no 9 there, that little tiny error won't cause a carryover in these first 5 digits. Okay? So that's the lecture for section 8.3.